So far, we've had a quick look at how type classes work in Haskell, and they're very much like an interface. They provide some functionality which a type must implement in order to use that interface or type class. For example, with the EQ type, we have to have double equals, the equality test, or not equals defined in order to be part of that type class. Today, I'm going to show you how to use another type class, the orderable type class. This is a type class which allows us to compare things like greater than, less than, greater than or equal to. And we're going to use that to implement a QuickSort algorithm. Now, we're going to do this not necessarily in the tidiest way at first. We're going to see later on how we can use other Haskell features to make it a little bit nicer and a little bit prettier. But just to remember, what the QuickSort algorithm does is, well, if we have the empty list or a one element long list, we finish, that's fine. Otherwise, we select the pivot element. So we select an element from the list. Normally we'll just go by the first element that we're looking at. So when we start, we'll look at the first element and then we'll move on to the next one. And we sort the list into two parts. We pivot around that. So we take the left-hand side of the list, the stuff that's lower than the pivot element, to be stuff that's less than it. And then we take the other side to be the things that are greater than or equal to the pivot element. So we wind up with the pivot in the middle, the things that are less than it on the left, and things that are greater than it on the right. And then we repeat taking new pivot elements until the entire list is sorted. So we're going to do this in Haskell. To do this though, first of all, I'm going to make a couple of basic helper functions. I'm going to do something that sorts through a list just to get us warmed up and takes the less than values. And then we'll do one that does greater than or equal to as well. So let's do less than. Now, I'm going to leave this generic at the moment. We're just going to say we want a list of A's. Or actually, no, we want an element A. We want a list of A's. And we want to return a list of A's. So we're going to take an element to check against the list, and then we'll return the rest, the list. So we'll say less than, and we'll say sort of some element A, and we're going to say in the empty list case, we return the empty list just as we usually would. When we're using recursion, we always want our best case, and that's usually the empty list when we're working on lists. Then we do x, A, colon, x's, and now we start to work. And this will be very similar to a lot of the functions that we have seen in Haskell. There is a reason behind that, but we've not seen how we can abstract away that detail yet. So at the moment, we're just going to have to work through the list as we usually would. So what do I do? Well, if I'm looking for elements that are less than, I say is x less than A. If it meets that condition, then it's true that it does fall into that sectional list. And then I want to keep that because this is the less than list. So then I do x colon less than A x's. And you could put some brackets around that if you want. And we'll define the next case. So the next case is when x is not less than A. So that's a case we're not interested in. That's a case where we just want to say otherwise less than A x's. And that's us. But again, as we've seen when we're working with type classes and polymorphic functions, we can be too abstract, and that's why we're getting an error here, because it says no instance for ord A arising for use in the less than or equal or the less than sign. So again, if we go into GHCI and now you do :I ord, then you'll see that we have this is the type class, which I've got a lot of fluff there, but it has the less than or equal to, greater than or equal to. Also comes with some min-max functions. And you can see here that the minimal definition is actually quite small, because if we just define less than or equal to, we can negate that to define greater than or equal to, and so on and so forth. So that's how we define that class. So we can't have this function using this operator unless we constrain it to the type ord. So I'm going to say ord A, and I've made a typo there, so let's, oh no, I haven't. So there we go. We're now constraining it only to the types of A, which are part of the orderable type class. And now we're happy. Again, this is the power of Haskell's type class system. We don't have to instantiate A. We don't have to say what A could be. We just need to say that A has to be part of orderable. And as long as it does that, we don't care what it is. We can work with any type of list. Now, of course, with QuickSort, we're likely to be working on integers, and that's probably what we'll use for examples. But we can make this function generic if we like. So let's do more than. And this is going to be extremely similar, so I'm just going to copy what we did above and go through that quickly. Now these are just helper functions. As I say, there is a neater way to implement this in Haskell. There's a very, very nice definition of this in Haskell, but we don't quite have the tools to do that yet. So we'll likely come back to this at some point and implement a nicer version of the quicksort without using these helper functions like this. And then we're just going to do the same thing where we say, okay, I'm going to say if x is greater than a, then, or if it's greater, if x is, actually what I want to say is if a is greater than x, that's the case I'm not interested in because I'm looking for elements that are bigger than a. So if a is greater than x, I don't care about those, and I just do less than a x's. And then the final case is the one where we're not, a is not greater than x, so I just do otherwise less than a x's, but I stick the element x on the front. So you can see this is me getting the getting the functionality for the two lists where I sort them on either side of the pivot element. So again, there are neater ways to do this, but this will do for the moment. And while we're here, let's just test this, make sure that our functions work, because that's what you want to do when you're working in Haskell or when you're programming in general. So let's do less than 5, and let's give it the numbers 1 to 10. And there we go, that looks good. And let's do more than while we're here. Oh, that's not quite right. That's because I was an idiot and I put less than instead of more than there. That's why we test our code. There we go. And you can see this is, Haskell makes this quite easy for you. You can just chuck your function in with some arguments and you see what happens. You don't have to worry about writing a main method or anything like that. So it's very straightforward. So make sure you test your code. Otherwise you'll make stupid mistakes like me. Now, let's do QuickSort. So I'm going to call it QuickSort. Now, the elements of this, we're not going to use greater than or less than directly, but we know that that has to happen at some point in the code because we're going to be relying on these functions to sort it. And if you think about this rough definition of quicksort that I've got up here, you can't really define quicksort without using the less than or greater than or equal to operators. So this is going to have to be part of the orderable type class. Again, orderable is just one that allows us to use those operators. And I'm going to take a list of A's, and I'm going to return a list of A's. So let's see, what do we do? Well, we're going to be working on a list. And we're going to be recursing because we don't have loops in Haskell. So what we're going to do is define our base case. And as usual, that is going to be the empty list. Now you could also define this as when you have a one element list, similar, it won't really make much of a difference. Hopefully by the time you've got down to a one element list, you've already done most of the sorting, or there's not really any sorting left to do. And if you do get to a one element list and you take out a pivot element, you'll see that that'll default to the base cases in the other two functions, so we'll be fine. So let's define the actual behavior. Now I'm going to name this a little bit oddly. I'm going to say p colon x's. Now remember in Haskell the common convention is to say the x cons x's. I'm saying p cons x's here because that's my pivot element, and I can name it whatever I like. So for the sake of just calling it the pivot, that's what I want to do here. So what do I do? Well, I know that I select a pivot element and then I sort the list around that pivot element. So I have the pivot in the middle, and then I sort on the left hand side to all the things less than it, and on the right hand side all the things greater than or equal to it. So in the middle I know that I'm going to have the pivot element, and on the other side I'm going to have two lists. So what I'm going to do, I can't use the cons operator because the cons would stick it on the front. So what I'm going to do is I'm going to say p goes in the middle, and we have this concatenation on either side. So I wouldn't use cons here because if I was consing it, p could only go at the front, and the pivot element could in theory go anywhere in the list. So we don't necessarily want that to happen. So if p, for example, is the greatest element in the list, the thing on the right here, the thing where things are greater than or equal to it, will just be the empty list. So if we stick it onto the empty list, we'll just get the element p at the end. So that'll be fine. So what do I do now? Well, I sort the list around the pivot element. So I want the less than on the left and the greater than on the right. But those things aren't necessarily sorted, so I'm going to have to recurse on both of those things. So what I'm going to have over here, because I know I want to work through the list, because I know I want to recurse, I'm going to have QuickSort. And now that takes a list. And now I need to figure out what that list takes. So what I'm going to say is less than. Now, I know that the thing on the left hand side has to be the things that are less than the pivot element, so the thing that I'm comparing against should be p. That's my a up here, so I'm saying that element should be the pivot element. I can reuse this name as many times as I want because it's now just a variable that I can pass around freely. Now I've checked the pivot element, so this should be x's. So now, here, I have a list of things that are less than p. And you can see this is very clean, this is very succinct. And of course, as I say, we can make it even more succinct. We can make this a very, very short definition if we're so inclined. And on the right hand side, I pull the same trick. And I say that more than, oh no, sorry, I shouldn't say more than. I should say QuickSort is going to be equal to, or is going to take as an argument, more than p x's. And that's QuickSort defined in Haskell. So you can see this is essentially a one-line definition. The only thing that stops it from being one line is the fact that we have an empty list here. Now, in Haskell, you could make this a one-line definition. You could use incredibly powerful higher-order functions, which we'll be getting onto later on, to make this even more concise than it is now. But as it stands, here are two very simple cases that work through the list, ensuring that we get the correct output. So let's reload this, and let's do quick sort, and I don't want to give it a sorted list, so let's give it a list of things I'm just going to make up and hopefully not put any typos in. So there's a bunch of values, and let's put a massive value at the end, and and 0. So we know that 0 is going to be at the front, and that massive value is going to be at the other end. And hopefully our quicksort will do this. And there you go. So as you can see, the power of being able to use type classes, function of or polymorphism, and Haskell's very succinct function code, is that we have something that would take you an entire class at least in Java. In C, I think the canonical definition for QuickSort is something like 60 or 70 lines of code. Here, we have something, the actual function itself is 3 lines. 2 lines if you don't count the type signature. So this is the power of Haskell. You can rely on abstraction, you can rely on telling the computer what it should do rather than how it has to do it, which is what would weigh down another programming language when you're defining this. As I say, I don't need these 2 functions to define QuickSort. I could do QuickSort in about 3 lines without these 2 functions if I was so inclined. These are here because we haven't seen those things yet, and we will see the things that allow us to make our definitions even more concise later on. But I would like you to spend some time getting used to this definition of QuickSort. It might look like we're abstracting a lot of the stuff away, but really I want you to look at this as saying, okay, you keep doing the same thing, that's what the recursive call is doing, and this is called less than, so this is likely to be a list of things less than p from x's, and this is likely to be more than things that are more than p from x's. So that's everything for today. I hope you found this useful. Of course, if you have any questions about anything I've covered today, please do let me know. Thanks.